the overall goal was to write some function whose dependent variable, the output, was a quantity we were trying to maximize or minimize, find a best value for of some sort. And so we did that by using the information we were given, and sometimes in some instances you're actually given that function. You just need to know how calculus can help you solve it, and how calculus can help you solve it as long as it's not too tedious is that at maximum and minimum values of a function, the derivative is going to be either 0 or undefined, or maybe it's at an endpoint of a domain that these best values occur. So there's just a few sort of spots to look. Endpoints you can find just by knowing where the endpoints of the domain are. Undefined points you can figure out where the derivative would be undefined, meaning sort of point or a cusp spot in a graph. You can find those by thinking about when where the domain of the derivative has issues, where that derivative wouldn't exist. And finding where a derivative is 0 tends to be, in most of the cases, other than the last one we did on Wednesday, tends to be just basic algebra situation. Most of the questions that we talked about involved, we ended up with a quadratic function, or maybe a rational function of some sort. Just the weird trig one we looked at. If you actually do take the time to go through and solve it with some trig identities, you can come up with the same result that we found, but like I said, it was going to end up being an endpoint of our domain, the 0 to pi. 0 was the ideal. So I didn't want to put us through all of that, and then that exasperation, if you worked really hard and it was just 0 was the answer. So in any case, the other sort of problem that we're working on relates to, this is a technique we're going to use, and it relates to if I have a couple of quantities that are changing in harmony, and I want to know how one is changing at a specific point in time, or how one is changing relative to the other. Sometimes we have two different quantities. I can think of one as a function of the other that are kind of interlaced in functions that might look kind of like this. Now, this is just an example of a weirdly structured, I put together an equation here, where x and y, shown as, again, the independent and dependent variables here, are intermingled in this expression, and you can see we don't get what typically you expect. Y isn't a function of x in terms of there's not a unique y value for any given x value. Sometimes there is, and sometimes there are multiple y values for one x value. But that doesn't mean that we can't express rates of change nonetheless. We can talk about how x changes with respect to y, how y changes with respect to changes in x, either way. And you can do that with any sort of function. It doesn't really matter which you declare dependent and independent. It's just on how you solve to find a derivative, what you consider to be kind of like the lead variable, and which you consider to be the independent or the input variable. So in any case here, this expression, we looked at it last time. We have this curve here, which, let me just click on it. When x is 2, for instance, there's, will it let me do it? There you go. When x is 2, we've got a point, let's see, just a little bit. If I can scoot this a little bit. Well, that's pretty close. We've got a point, x equals 1.99963, and y is about 2. But if we zoom out, we also have other points where x is 2. And the behavior at the graph at those two different points is extremely different. Actually, that might be 3 points. But at this point, the graph is nearly flat, or in terms of if you just saw this immediate area, you'd say, oh, the rate of change of y with respect to x is essentially 0 near that point. Well, if I'm looking down here, which I think if we zoom in down in this area, we're going to see we have actually a couple of points. Let me zoom in. Yeah, when x is 2, let me scoot this a little bit. It's about as close as I can get this way. I've got two y values that are pretty close together, but there's one here and then one down below this straight line at x equals 2-ish. Let's see. Well, that's about as close as I can get. Goes through a couple of different y values, so this straight line passes through the curve twice there, as well as the once above. But in either of these places, well, this bottom one, it looks like an extremely negative slope, and the upper one, an extremely positive slope. So just thinking about rate of change of y with respect to x, I've got a high positive number, a very negative number, and then one near 0 up at the point near the top of the curve. So we should be able to find those values of the steepness of this graph, whatever the quantities x and y might represent here, how one changes with respect to the other, despite the fact that this relationship isn't structured the way that we saw them earlier. So how we're going to do that, let me just give ourselves some more working room here, is if you can imagine that even though this function is in such a way that it'd be either really difficult to or impossible to separate precisely x and y just using algebra skills. So I can't really get y by itself and solve for x. I mean, if I wanted to get these two terms with y on one side and then I could move this x over there, it might look closer to normal. But the thing is, I can find a derivative of y with respect to x for this thing regardless of what form it's in if I have x's and y's. So my goal is going to be here to find our standard rate of change of y with respect to x, so that it represents our standard, we could find it the other way around also, by the way, so that we could find the standard like slope sort of idea. So this would be a large positive number. Y changes a large amount for small changes in x in the positive direction here. Small changes in x in the positive direction here would be going down the curve, and here would be going up the curve. So it's a little bit different in that sense of imagining going all the way across the curve, but regardless, what I'm going to do to find this is imagine that I can have y written as a function of x. So I'm just going to write, suppose that y is some function of x. We're going to pretend that for a minute. Or in other words, looking at this expression here, imagine that instead of it being x squared plus y cubed, imagine it was x squared plus, well, instead of y, I'm going to call it f of x, some whole function. If I were able to solve to get y equals an expression only in terms of x, I could call that f of x. Now, it wouldn't actually still be a function here, but f of x cubed minus 2x times f of x equals 7. Now, this, I can't solve this for f of x either, but if you think about the terms of the expression on the left, each of those terms are things that we have found derivatives of before. So the derivative of y, we typically write when x is the input variable as dy dx. The derivative of f of x we typically write as f prime of x. So if I'm imagining that y is the same as this mystery f of x that I just inserted, then finding dy dx is the same as finding f prime of x. And if you can imagine, even though I don't know what f of x is written out as a function rule, I don't know its rule, I can still take derivatives of things that look like this. That would just involve chain rule. If I said take the derivative of some whole formula squared or cubed or whatever, you think, oh, well, use power rule and then times the derivative of that inner function. So if I were taking the derivative of this term, if that were the whole function rule for something or another, so I'd take the derivative of this with respect to x and say, oh, well, that's 3 times whatever the inner function is squared times, chain rule, f prime of x. Okay. Well, if I told you just take the derivative of x squared, that's easy. That's like day one of derivatives. That's just 2x. And if there were, a couple of terms added or subtracted, we know the addition and subtraction rule. So taking the derivative of these two terms is 2x plus 3 f of x quantity squared times f prime of x. Now I'm going to take the derivative of this third term here. Look at the structure of it. What derivative rule are we going to have to use? Product rule. So I'll just keep the 2 mashed with the x. You don't have to have it as a 2 and an x and an f of x. But I wrote the negative down already, so I'm going to write the rest of this in parentheses, or brackets rather, whatever, grouping symbols. But I need the derivative of the first 2x times the original f of x plus, other way around, the original 2x times the derivative of f of x, f prime of x. So that left-hand side is all nice. What I've done is take the derivative of each of the 3 terms, Now our actual goal is to take the derivative of not just a series of terms using derivative rules, but to take the derivative, or somehow find a derivative relationship. We have an equation here as opposed to a function. We have x squared plus y cubed minus 2xy equals 7. And what we've just done so far is find the rate of change of the left-hand side of that expression. Well, if I have an equation where the left-hand side equals the right-hand side, meaning they represent the same thing, or in other words, this left-hand side, no matter how weird it looks, no matter what x's and y's I'm using, I'm only allowed to use x's and y's such that this left-hand side equals 7 all the time. Or on that purple curve shape, which I'm zoomed into right now, at every single point on that, x squared plus y cubed minus 2xy comes out to have the same value, 7. So when I change x's and y's, trying to find rates of change of that, well, these terms all change strangely, but if these two expressions are equal for all the x's and y's I'm concerned about, then the rate of change of the left-hand side is going to be equal to the rate of change of the right-hand side. Which, what's the rate of change of 7 with respect to x? 0, right? It's a constant. So this is one of those, it's another thing, just thinking like algebra things. As long as you do the same thing to both sides of the equation, you're okay, as long as it's not an illegal divide by 0 or something like that. But if this expression on the left is equal to this expression on the right, for all values of x and y that I'm concerned about here, then the rate of change at any of those same points is going to be equal to the rate of change of the right-hand side, which is 0. So meaning, okay, I have this expression. Now how this is different from other derivative taking we've done is we're not done yet. We have some algebra to do. The goal of this was to find dy dx, otherwise known as f prime of x. But notice that we have an equation now that has f prime of x in it as a couple of terms. So all we have to do is solve for f prime of x, meaning isolate it. So we've got some terms that don't have f of x or don't have f prime of x in it. You know, subtract, divide, those sorts of things to solve for f prime of x. Meaning like this 2x term, you can move that over to the other side of the equation. So I'm going to move this over by subtracting. This term I'm going to leave here because although it's messy, it's got an f prime of x in it. So does this one, although it's after a negative sign. This term here, though, 2f of x, doesn't have our f prime in it, so I'm going to move it to the other side. Since it's actually negative 2f of x, I'm going to add 2f of x. So we've got some strange looking variables, but all we're going to be doing is like linear equation algebra solving at this point. Because notice f prime of x is just a linear appearance here multiplied onto some other stuff. Same here, it's just multiplied onto some other things. So if we do this reorganizing algebra style, what we're going to have is on the left side of this equation, just because I isolated it that way, actually let me scoot this down a little. On the left-hand side, we have this 3f of x squared times f prime. And then minus 2x times f prime of x. And on the other side, we've got negative 2x plus 2f of x. And the order of the terms, they're just added and subtracted. Obviously, you could write those in different orders. But our goal is to solve for f prime of x. So, well, it's really divide, but factor and divide. I could write this left-hand side as f prime of x times 3f of x squared minus 2x, right? And so just to solve this, we get to divide by the stuff that I've written in brackets here. So f prime of x, by dividing by that expression in brackets, we have a formula for f prime of x would be this. I'm just going to reuse this. Sorry for the messy algebra style here. F prime of x equals, and I'm going to box this, negative 2x plus 2f of x over 3f of x squared minus 2x instead of rewriting that. Here's our expression for f prime of x. Now, just as a note, f wasn't in the original expression. I just kind of rewrote. F of x means y, and f prime of x means dy dx. So if we wanted to use the original variables to write this, we could do that also. Using the original symbols, this would be dy dx equals negative 2x plus 2y over 3y squared minus 2x. And again, you could write the terms as addition and subtraction. You could write that a different way, like numerator 2y minus 2x, or you can factor out the 2 if you felt like it, but it doesn't reduce. But in any case, we have an expression for dy dx. It involves having to know both the x and the y values, like we talked about, because this isn't y as a function of x, where for any one x value there's only one y. So just given an x value, we wouldn't necessarily know which y position on the graph we're talking about. But at the spots we were talking about earlier, let's see, negative 2x plus 2y, 3y squared minus 2x. Looking at that graph, we had a few spots where x was 2. Where x was 2, one of them had a derivative essentially 0. And you can maybe see from this, oh, maybe it was the point when x was 2, y is also 2. So that point 2, 2 had a derivative essentially 0. Whatever that denominator comes out to be 0 over something. When we had x is 2 and y was something else down near negative 2, our derivative comes out to be extremely positive or extremely negative, depending on exactly which y value we were talking about. So in any case, the point of this is that regardless of the arrangement of x's and y's, or input and output variables, whatever you want to call them, if we're doing a graph, whether they form a function or not, we can still express rate of change of y with respect to x when that makes sense, graphically speaking. So if there's, if the function doesn't exist, like if we're talking about kind of like on the wrong side of an asymptote of a log function, where the function isn't there, or past the domain of a square root function, we can't deal with that. But for any other sort of relationships for x and y, or whatever two variables you want to call them, if the graph exists there, if we can find those coordinated points, the xy correspondence points, and see a pattern, we're like, oh, this seems to be decreasing, or this seems to be increasing, or this seems to be, as x increases, y is essentially staying constant. Or maybe as x changes, y is changing drastically in one direction or the other. Regardless of what it is precisely that's going on, if we can see something going on, we should be able to describe that rate of change by finding a derivative. It's just sometimes that finding a derivative is a little bit weirder of a process than others. The same technique can help prove things like logarithm rules and power rules and stuff in general. We'll talk about that maybe next week. Kind of an extra related topic. But let me get back to this guy. But let me just show you a couple other examples. Here, I'll just use this blank screen here. A couple other examples of implicitly defined relationships, or things that we've even seen before, where you obviously could solve for y, but it comes out the same. So for instance, if I had the relationship 2x plus 3y equals 18. Obviously, I could rearrange this and have y equals, what, negative 2/3 x plus 6, just subtracting and dividing. So I'd have negative 2x and then divide by 3. And I know that the derivative of this y with respect to x is negative 2/3 because that's an easy function. But just for comparison's sake, let's say I just left it in the form that's kind of similar to the messy problem we just did. I can find the rate of change of y with respect to x without rearranging this, and I'll get either an equivalent answer in some slightly more complicated forms, or exactly the same answer in the case like this. If I think of y as a function of x, and I can even, you can do this mentally, or you can physically write it out, 3 f of x. If I have this relationship here, that's true if I take the derivative of both sides, the rate of change of both sides with respect to the same variable, x we'll use, then I should be able to solve to isolate to find that dy dx, or f prime of x in this case. So the derivative of 2x with respect to x is 2. The derivative of 3 f of x, that's just a coefficient 3. The derivative of f of x is f prime of x. And then don't forget about numbers. The rate of change of this right-hand side is not 18. That's its value all the time, so it is never changing. And so you can see if I solve, like we did in the last one, much more complicated case for f prime of x, it'd just be subtract 2 and divide by 3. So 3 f prime of x is negative 2, so f prime of x is negative 2/3, which is what we'd expect, because this is a linear function with a slope of negative 2/3, constant rate of change, negative 2/3. So it doesn't matter the difficulty level of the problem. You never have to rearrange these if you don't want to. If I have things that are slightly more jumbled, or just we know they're not functions, something like x squared plus y squared equals 9. This is a circle with radius 3 centered at the origin. Not a function of y with respect to x or x with respect to y, but there are steepnesses that I should be able to evaluate, or rates of change of y with respect to x at every point around that circle. At a couple of points, the left and right edges of the circle, that rate of change would be undefined, but I could still determine that from the function itself, from the derivative function. But just thinking about this, I'm going to use a different notation. Instead of writing in f of x here, I'm just going to remember that the derivative of y is dy dx. If I want to find a rate of change of y with respect to x, we're treating x as the independent variable, or the input variable of the function, and y as the name of the function, or, so like the f of x was before. So if we're doing this, then the derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x, or the derivative, y squared, when we're trying to find the rate of change of y with respect to x, means that y is being treated as a function name. So this is like f of x squared. The derivative of a function squared is 2 times that function times the rate of change of that function. So I could have done what I've done in the other cases and called this f of x squared, but y and x here aren't being treated equally. X is being treated as a simple variable, and y is being treated as an entire function. And that's what we mean when we say the rate of change of y with respect to x, is that y is this quantity that's dependent on x, or it's a whole relationship based on x. So x is easy to find derivatives of, y involves chain rule, if you want to think of it that way. But this is differentiating both sides, and if I want to solve for dy dx, it's subtract and divide. And this one's, again, maybe simple enough to do all in one step. Subtract 2x, and then divide by 2y. And you can see this even simplifies to negative x over y. Now, this was, I said, it's like a circle. Let me draw a circle first. Center at the origin, radius 3. So I know it's got points at like 3, 0, 0, 3, etc., and lots of other points that are less easy to find. But if I look at the rate of change, negative x over y, if I'm at this spot, 0, 3, I can see that the rate of change at that spot would be negative 0 over 3. Well, that makes sense. Negative 0 over 3 is equal to 0. Rate of change at this top spot as x increases, y stays essentially constant when we're at the top. It's not increasing or decreasing right at the peak of that circle. If I were at a point like 3, 0, and I thought about the rate of change there, visually speaking, I see, oh, that's a vertical line, undefined slope in terms of like algebra stuff. But using this rate of change of y with respect to x, if I substitute in 3 for x and 0 for y, I get negative 3 over 0, which that's an undefined valued function, or an undefined valued expression, rather. And similarly, the slope of this tangent line it's not positive or negative, it's undefined just for a moment. It's not that the function is undefined there. It's just that the rate of change is undefined for a moment, at the moment when x is 3 and y is 0. And that's the only place where x is 3. But there are multiple places where x is any value between -3 and +3. There's 2 y's that go with each of those. But in any case, we can find these rates of change of y with respect to x with or without solving. Notice this one's pretty easy to solve for y, it just makes a messy square root sort of function. But I did want to point out it actually turns out to be the same, just in a different form. So let me just give ourselves some extra room here. So if I were to rearrange this x squared plus y squared equals 9 equation, let me make this a different color. X squared plus y squared equals 9. Let's solve for y. That would be y equals, I do 9 minus x squared and then take the square root. Now, if I take a square root, I'd only get the top half of this. So I'm going to put plus or minus, but I'm going to ignore that for the time being. Using our derivative rules, we were only taking derivatives of functions, but this is plus or minus that. So if I were to try to take the derivative of this expression using standard, mastery test sort of rules, dy dx, I've got a square root function, so that means 1 over 2 times the square root of this, 9 minus x squared, times the derivative of that inner function, chain rule. Derivative of 9 minus x squared is -2x. And if you can see, here I'll just do this, you can reduce this factor of 2, and we'll end up with -x over square root of 9 minus x squared, which that doesn't look quite the same as this, but -x over y and -x over 9 minus x square root of 9 minus x squared, when y is equal to square root of 9 minus x squared, they're equivalent, just written in different forms. So in terms of implicit derivative taking, and that's what this is called, finding an implicitly defined function's derivative, because it's implied that y is a function of x, or whatever the dependent variable is considered to be the top part of the rate of change expression. Finding those, sometimes you can solve for that dependent variable, sometimes you can't or don't want to, but the result comes out the same either way as long as you're careful about finding the derivative implicitly. If you do leave them jumbled together, remember each time you encounter that y variable or the dependent variable, think of that as representing an entire function, so you get to use chain rule most of the time. All right, so moving on then. If you looked at your textbook, this should look familiar. We've got a mischievous monkey kicking a ladder, and it's a 10-foot ladder. It was against the wall, and he kicks it away so that it falls down. Now, it's kind of falling in slow motion so that we can watch it. But if I want to know how y is changing with respect to x, and using x and y as, well, x, the distance at the bottom is from the wall, and y is the distance that the top of the ladder is from the floor, since the length of the ladder is 10, we can talk about how x changes and how y changes over time. As x grows, y is shrinking, right? Because this is a fixed 10-foot ladder. So as the bottom gets farther from the wall, the top has to slide down to accommodate that. But we can actually describe the relationship between how those two change. And if you can see here, we've got a right triangle. I'm labeling one side of it as x, one as y, and then the hypotenuse is 10. So if I want to find how y is changing with respect to x, it's exactly the sort of thing we just did. In fact, it's exactly the problem we just did. Meaning, to determine y prime, or dy dx, I need a relationship between x and y, which that'd be x squared plus y squared equals 10 squared, right? Which is almost the same as what we had. We had x squared plus y squared equals 9, but same general thing. If I have a relationship between two quantities' values, I can talk about how one changes with respect to the other. whether or not those two form a standard like function where one is a function of the other or the other is a function of the first in the standard definition of a function, if I can find a relationship between them, regardless of the type of relationship, I should be able to model then how one changing affects the other. So I can think of taking the derivative of both sides of this. So derivative of x squared and derivative of y squared. This is exactly what we just did. We had x squared derivative plus y squared's derivative equals 10 squared's derivative, which is 0. But again, since we're finding the rate of change of y with respect to x, we're treating y as if it's a whole function and treating x as a simple variable. So when we take the derivatives of these two parts, it's not kind of a symmetric treatment. X squared's derivative is 2x. A function squared, when I take its derivative, is 2 times that function, and then chain rule, times the derivative of that function with respect to x. Or, as we said, it's not actually a function, but it turns out the same. So, in any case then, doing the same solving we did before, y prime would be negative 2x over 2y, which simplifies to negative x over y. Or, in other words, for circles centered at the origin, doesn't really matter how big they are, the derivative of y with respect to x comes out to be the same expression every time. Larger, if you want to think of this as a circle with radius 10, you can see it's the same as the circle with radius 3 that we just dealt with. Exactly the same by the time we're at the end. Now, the xy coordinate points on it are different, but the relationship between changes in x and y come down to the same xy formula. We just would be picking different x's and y's to substitute in. So, in any case, this explains how, as this bottom slides out, how the top changes. Or how as x increases, it'll tell us how y decreases. And you can see in this formula, as x increases, this numerator of our derivative becomes more and more negative. Y, we know, is going to have to decrease whenever x increases. So the denominator is getting smaller, and the numerator is becoming more and more negative. So I've got a negative number divided by a positive, and it's becoming more and more negative divided by a smaller and smaller positive, meaning that the rate of change of y with respect to x, as x gets larger, that rate of change is becoming more and more negative, or in other words, y is moving downward more per little change in x at the end than it is at the beginning. And you can maybe see that. At the beginning, if you watch this, I'm just sliding this along, it hardly looks like y is moving at all. As x moves a little bit to the right, a little bit to the right, you can hardly see y moving at all. But once I get farther to the end, moving x just a little tiny bit, y jumps more, and I can see that, well, I'm at maybe like x equals 8 right now. Y is still above 5. In the next couple of units moved for x, feet, y is going to have to drop the rest of this way, because I know when x gets out to 10, the ladder is going to be all the way on the ground. So this rate of change of y, as x continues moving, I can imagine x continuing at a constant pace, which is maybe not quite accurate physics-wise. We're going to talk about that. But y is going to drop more per x. Per little tiny change in x, y is dropping more and more quickly at the end, and I couldn't even make it go any slower than that. So I just have something that's more and more quickly. More and more quickly would represent something to do with time. If you notice, time is not actually involved here. This is just, we're just talking about how y changes with respect to x. So if x moves an inch, we can talk about how far y moves. And x moving an inch when x is near 0 is very different from x moving an inch when x is near 10 in terms of how that affects y. X moving an inch at the beginning, oh, y shrinks a tiny bit. Much less than an inch. If x moves an inch when x is like near 9.5 or 10, y is going to move much more than an inch. It's going to probably drop maybe even a foot. But this rate of change, this is a rate of change of y with respect to x. And as I said, it doesn't involve any like meters or feet per second or anything like that. But let's pretend it did, because that's a whole different question. Here we go. New question. How fast is the top of the ladder falling in feet per second? This is asking a different question. It's actually giving us kind of more symmetry to the question, more symmetry in terms of how x and y are going to be treated. So what we'd like to do, x is the distance that the bottom of the ladder is away from the wall, and y is the distance that the top of the ladder is away from the floor. And it's moving downward, we know, and the bottom is moving outward away from the wall. But suppose that we imagine time. We're going to put time into this, and the monkey's going to kick the ladder, and then we're going to measure how much time has gone by. Which you can kind of, as a video, you can just kind of imagine those are number of seconds since the monkey kicked the ladder. But suppose that the bottom of the ladder, when the monkey kicks it, somehow is able to slide out at a constant rate. Now, it's kind of unusual. Maybe the floor is waxed just right and has enough bumps in it so that it gets kicked and the bottom slides at a constant pace. But just to simplify this problem and confuse issues of physics for a moment, suppose that we have that same idea and the bottom is sliding out at a constant rate of change with respect to time, and we'll call that rate v feet per second, like v for velocity. So I can think of x, the distance that the bottom is from the wall, as a function of t. So I can call it x of t. X is a function of time. So after 1 second, if it was at this constant rate, v feet per second, the bottom would be 1 foot away from the wall. After 2 seconds, it'd be 2v feet away from the wall, sorry. After 3 seconds, it'd be 3v feet away from the wall. And any number of fraction of seconds, however much time has gone by, the distance that x is, or that the bottom of the ladder is from the wall, or the length of x, would be whatever that amount of time is, times v. But we don't actually have to write out the formula for x of t. We'll just call it x of t. And I know that the rate of change of x with respect to time, dx dt, or x prime of t, is just this constant v. All right, this sounds like it's getting very confusing. It actually makes it a little bit easier. In this function here, we're imagining x as a function of time. That means y is going to be a function of time also, a different function. We'll call them x of t and y of t. And so just changing this nice, simple Pythagorean theorem-looking equation into something that looks messier actually makes this, A, more symmetric in terms of finding derivatives, and B, maybe makes more sense in terms of rates of change. Because lots of times we think rates of change and, like how fast something's changing, as opposed to how one thing changes with respect to another's measurement that isn't time. But looking at this, if I want to know the question here, how fast is the top of the ladder falling in feet per second? Well, I want to find an expression for y prime of t, or dy dt, something like that. So you can use whatever notation you want. But if I take the derivative of this, derivative of x of t squared with respect to time, so I can find speeds with respect to time, like feet per second, would be, oh, well, x is a function, so x of t squared, its derivative is 2 times x, or 2 times x of t, times the rate of change of x of t, dx dt. And same with y. Y is also a function of time, so its derivative with respect to time is a part of this, 2y times y prime, or 2 times x prime, if you want to use kind of shorter notation. But we're thinking of x and y as both functions of time here under this new question. So x and y are both changing as time goes on. As x gets larger, y gets smaller, but instead of measuring a change in x relative to a change in y, we're talking about, well, what time is it? How much time has passed? And then we can talk about how fast each of them is changing, in fact. So if I want to know how fast is the top of the ladder falling in feet per second, I can just do a little bit of algebra. Again, it's just subtract, divide sorts of things. So if I wanted to find dy dt, how fast the top of the ladder is falling in feet per second, it would be subtract the x term over, subtract 2x dx dt, and then divide by 2y. We get the same sort of expression as we did before, only instead of dy dx is negative x over y, we have dy dt, or y prime of t, is this same xy relationship times dx dt, which dx dt, rate of change at the bottom, is this constant v. This is known as, oh, let me write that down because I forgot I didn't put that on here. So the rate of change of y with respect to time, meaning like a speed at which the top of the ladder is moving down the wall, because it is moving down, is given by negative x over y times, well, it says dx dt, but we're given a value for that, times v. V feet per second is how fast the bottom is sliding out. So this v is a particular value of dx dt, and in fact we're told that it's through this process, it's a constant value. You could treat it either way. But I've got this rate of change of the height of the top of the ladder with respect to time, or in other words, how fast this is falling downward, and it is going to be negative because x's and y's are going to be positive. This is a constant speed. Speeds are always positive, well, 0 or positive. So this expression here is going to be something negative for all the values of x and y that makes sense in this question. So it wasn't actually a circle. We were talking about a triangle with side lengths x and y formed by a ladder with hypotenuse 10. So this is always going to be some negative number, and depending on what x and y we've picked, it's going to be different negative numbers, although I don't know the value of parameter v. If it's a speed, it's something 0 or bigger, and in the picture we know it's not 0. So we've just got some sort of negative value that changes as x and y change because of this fraction here. And this is what's known as a related rates equation, because if you can see, the first equation, x squared plus y squared equals 100, relates to quantity lengths, relates the two distances measured away from the wall by the ladder. By the time we've taken a derivative of it, we have two rates that are related, a rate of change of the height up the wall with respect to time, and a rate of change of the bottom away from the wall with respect to time. So feet per second that the bottom moves away from the wall, feet per second that the top slides down the wall. We're relating these two different speeds or rates. So this is what's called a related rates equation. And we get those by starting from an equation that relates a couple of quantities and taking their derivative with respect to, most often, time, some third other variable, which means that we have two things that we're thinking of as just an input and an output, or an x and a y, and suddenly we're treating, well, these both change over time. So we've got actually a third variable, and both of the first two are functions of that third variable. So we've got an independent variable of time and two dependent variables. So sounds like a complex process, but it just kind of makes the implicit derivatives we're dealing with kind of more symmetric, because the x's and the y's are the things we're related are both functions of something else. And so we're using just a lot of chain rule. So this is what I just said. The source of a related rates equation is an equation that relates the associated quantities, in this case lengths or distances measured with the ladder. And to get a related rates equation, you start from that, and then you take a derivative with respect to, and every single problem in the homework is this, with respect to time, how it changes over time. The rates that are measured here, it could be some other quantity, but all the problems in the homework are that the third quantity that's involved, that they both change with respect to, are over time. So we have speeds of things happening, or velocities at which things happen. So, clear that off. So for instance, suppose the edges of a cube, I've got some projection on a screen. It's a cube, somebody's like computer programming homework. Make a cube and then make it grow at a certain speed. So trying to make this so that, in specific, the edges are getting longer at a rate of 2 centimeters per second. We want to know how fast the volume is changing when the length of each edge is 50. Now, all those numbers at the end, that's not really going to help us write our equation, but we can tell from this. I want to know how fast one thing's changing based on knowing some other speeds or rates. So there's a whole bunch of rates. They're related somehow, because I know that the edges of a cube getting longer will affect the volume. It'll make the volume get larger. But the edges are getting faster at a certain rate with respect to time, 2 centimeters per second. So the volume's also getting larger at a certain rate, maybe not a constant rate all the time, and we'll figure that out. But again, the idea here is if I can relate the underlying quantities here, the edge lengths of a cube and the volume, then I can take a derivative of that relationship with respect to time, or in other words, the edge lengths are a function of time, and the volume is also a function of time. Let's figure out how the rates of change of those are related. So just looking at this, well, cube. I'm not going to try to draw a cube because it'll be really messy, but cube, how do you find the volume of a cube? You just take the edge length and cube it, right? Volume equals, I'm just going to say, I'm not going to write E cubed for edge length, I'm going to say X cubed. So I'm using X here as an edge length in centimeters, and V as the volume in, it would be cubic centimeters, volume of the cube. So if I wanted to figure out how, if I know how fast X is changing, I want to know how fast V is changing, and it's at a particular point in, well, not in time, but at a particular point in the process when the volume happens, or when the edge lengths happen to be 50. What I'm going to do is imagine V is a function of t and X is a function of t. Both of these are changing over time. They're not the same function. And I could write out X as a function of t, write out that function. But if I want to know how the rates of change of volume and side length are related, then I'm going to take the derivative with respect to time. So taking this derivative, I get 3 x of t squared times the derivative of x of t. So here's our related rates equation. I related one rate to another rate, the rate of change of x and the rate of change of v with respect to time. To answer this question, though, how fast is the volume changing? That's asking us to find this. How fast is the volume changing? When the length of each edge is 50 centimeters. Well, the length of an edge is x. Well, so at some point in time, I don't know how many seconds, x of t is equal to 50 centimeters. X prime of t, I actually know the value for. It's 2. 2 centimeters per second. So we're supposed to find v prime of t, and you can see it's equal to 3 x of t squared times x prime of t. And I know the values of both of those pieces in there. So v prime of t, just by substituting in, is 3 times 50 squared times 2. Now, I don't know what that number is off the top of my head, but this is a number, and the result would be, you can even see from this, this would be centimeters squared times centimeters per second. So this would be in centimeters squared times centimeters per second, whatever this number is. So I'll let you figure that out if you want to. But I'm going to stop at that for today. I have something to pass out to you, which is a take-home quiz for the weekend, not on related rates. It's on optimization. You also have your iMath AS optimization questions. It's just 2 questions with a lot of space to do your work in. But make sure you don't leave here without one of these in. And if you have questions, please make sure you check into office hours or email somebody between now and Monday when this is due.